Good morning, dear students, and welcome back to our course. In the last lecture, we discussed in detail about the concept of transfer function, and we defined transfer functions in different way. So, first definition to define transfer function is nothing but it is the ratio of two polynomial in S domain by assuming all initial conditions to be zero, or transfer function we can also define as a parametric function that depends on system parameter only, and it does not depends on the type of input and the output generated by that particular system. That means it is a kind of function that defined by the system parameters only. And third definition, which is one of the most important definition, and normally we implement that definition to find out the expression for transfer function for any given system, is that it is defined as the ratio of Laplace transform of output to the Laplace transform of input by assuming all initial conditions to be zero. This is very important. And mathematically, we derive the expression to find the transfer function for any general physical system. So we can write here as transfer function is nothing but the ratio of C of S whole divided by R of S by assuming all initial conditions to be zero. This is very important, where C of S indicate the Laplace transfer or Laplace transformation of output, and R of S indicate the Laplace transformation for the input. That is important. And sometimes in some cases transfer function is also defined as the process of finding the efficiency of the system in frequency domain. Why? Because if you see the definition of transfer function, it is nothing but the ratio of output by input, and the ratio of output by input is nothing but what? Efficiency. But we are trying to define output as well as input in terms of frequency, in terms of S domain. That's why in some cases transfer function is also defined as a process of defining the efficiency of a system but in frequency domain. So these are some terminologies through which we can define the concept of what? Transfer function. Now what informations we can get from transfer function? Number one, through transfer functions we are in a position to find out what are the poles and zeros of the system. Now, what is pole and what is zero? Poles are nothing but those complex frequency where if we try to find the magnitude of transfer function, it is going to be equals to what? Infinite. So, those complex frequencies where the magnitude of transfer function is going to be infinite are called as poles. In the same way, what are zeros? Zeros are those complex frequencies where the magnitude of transfer function is going to be zero. So those complex frequencies are called as zeros of the system. And normally to find the zeros, what we need to do? We need to equate the numerator polynomial function of the transfer function to zero. In the same way, in order to find the poles of the system, we need to equate the denominator polynomial function to zero. That is important. So this is the very first thing that we can collect if we know the transfer function for a given system. Then second point which we determined from the transfer function is nothing but the overall system gain, K. What is the overall system gain? That we can also identify through transfer function. Then third thing is we are in a position to identify what is the order of the system as well as what is the type of the system. In the coming sessions, we are going to discuss in detail about what exactly the meaning of order and what exactly the meaning of type. But for time being, let us consider that if we know the transfer function of a system, we are in a position to identify what is the order and what is the type of the system. That is important. Then if we know the transfer function of systems, we are in a position to identify whether the system is stable or not. That means in order to find the stability of a system, first and the most important thing is that we must know its transfer function. It may be open loop transfer function, it may be closed loop transfer function. But the thing is that in order to find out the stability of a system, by applying any logic, it may be Routh-Hurwitz criteria, or it may be root-locus technique, or it may be Bode plot technique, or it may be Nyquist plot or polar plot. The thing is that while applying these techniques to find out the stability of a system, we must know the transfer function of a system. Hence, transfer function plays an important role to identify the stability of the system. That is very important. Through transfer functions, we are also in a position to find out the characteristic equation. Now, what is characteristic equation? Characteristic characteristic equation. Actually, characteristic equation for a closed loop transfer function is nothing but 1 plus minus g of s into h of s, that is going to be equals to what? 0. For a negative feedback system, it is going to be plus. For a positive feedback system, it is going to be minus. So 1 plus minus g of s into h of s is equals to 0. And the roots of the characteristic equation plays an important role to find out the stability of a system. That is very important. So once we know the transfer function, through transfer functions we are in a position to find out the characteristic equation, which is also called as the denominator polynomial function of the transfer function. And through characteristic equations we are in a position to find out the system stability. So these all informations we can collect about the system if we know the transfer function of the system. Hence, it is very essential for us to study what are the different types of technique through which we can find out the transfer function or the expression for transfer function for a given system. I hope this point is clear to everyone. And then in the last lecture, we also started uh, solving numerical on transfer functions, and we derived the mathematical expression for any physical system. So the mathematical expression of transfer function for any physical system is finally uh, in the form of like k, where k is nothing but the overall gain of the system. Then here we are having some numerator polynomial function, which we define, I think, in terms of n, or it is nth order numerator polynomial function. And then here we are having denominator polynomial function of order m. That means here we are having the power s to the power n, and here we are having the power s to the power m. And finally we make a comment, that means the relationship between m and n. And finally I told you that the value of m is always more than n, or at the max equal to n. That means the number of poles available in system are always more than number of 0, or at the max they are nothing but equal. So this logic is applicable for all kind of physical system. That is very important. That means if you take any physical control system, number of poles are always greater than, or at the max they are going to be equal to zeros. The reverse situation is not possible. That means zeros are more than poles are not possible. So this point you have to remember. And then we started numerical on uh, how to find a transfer function for a given system. So in today's class, first we will discuss what is the concept of pole zero plot, or how to represent poles and zeros in S plane, and then we are going to solve some numerical on that technique. So as I told you that poles are nothing but those complex frequencies. They are nothing but those complex frequencies where the magnitude of transfer function is going to be equals to what? Infinite. In the same way, zeros are nothing but those complex frequencies where the magnitude of transfer function is going to be 0. Normally, poles are indicated by a symbol cross. This is very important. In S plane, for example, if you are interested to uh, represent the poles of a given system in S plane, so normally we need to use cross symbol to indicate poles, or the poles of the transfer function. In the same way, zeros are indicated by symbol circle in the S-plane. So these are the standard representations or standard symbols that are used to represent poles and zeros of a given system or of a given transfer function in the S-plane. So let us try to identify and solve some numerical. If you have a transfer function of a system, how to find out its poles, how to find out its zeros, and then how to represent those poles and zeros in the S-plane. That is important. So suppose we are having the transfer function of a system like this. So transfer function, let me change the color. Okay. Now suppose the transfer function of the system is given to us. It is like g of s by r of s, and it is going to be equals to 1 by 2. Then we have some function in the numerator and some function in the denominator. So the function available in the numerator, which is called as numerator polynomial function, is s square plus 4, then in bracket 1 plus 2.5 times s. Then we have some function in the denominator, that is s square plus 2 in bracket 1 plus 0.5 into s. And here our objective is to find, number 1, poles of the system, number 2, zeros of the system. Then we need to indicate poles and zeros in S plane, and we are also interested to find the magnitude of transfer function at a complex frequency of s equals to 2. This is what our objective is. So here our objective is, we have the transfer function represented by this expression, and our objective is to find poles. Then we need to find zeros, then we need to indicate those poles and zeros in the S plane, and then we need to find the magnitude of transfer function at some complex frequency, and the complex frequency is s equals to 2. So how to solve this numerical? First, as I told you, that in order to find the value of poles or in order to find the value of zeros, first of all we need to focus on the numerator polynomial function as well as on the denominator polynomial function of the given transfer function, and then we need to equate those equations to 0, and then we need to solve those equations for s. Okay, so apply that logic over here. So I can write here calculations for zeros. So in order to calculate the value of 0, what we need to do? We need to equate this numerator polynomial function to 0, because I told you that zeros are nothing but those complex frequencies where the magnitude of transfer function is going to be 0. And this is possible when we equate the numerator polynomial function to 0 and try to solve this particular equation for s. So those values of s are nothing but zeros of the system. So what to calculate or to find the value of zeros, what we need to do? We need to equate numerator polynomial function to 0. So numerator polynomial function is s square plus 4, then in bracket 1 plus 2.5 into s, that this term we need to equate it to 0. And then if you solve this particular expression for s, what you will get? So if you equate this particular term to 0, it will be like s square plus 4 is going to be 0, or I can write here as s square is going to be minus 4, or I can write here as s is going to be equals to square root of minus 4 with plus minus, or I can write here as s equals to plus minus square root of minus 4 is nothing but your j times 2. I hope this point is clear to everyone. So s is equals to plus minus j times 2 is nothing but the zeros of this particular system. In the same way, we need to equate this particular term to 0. So if you equate this particular term to 0, that means 1 plus 2.5 into s is equals to 0. So I can write here as 2.5 into s is equals to 0. Is minus 0.4. So finally, what we conclude that for this particular system, the zeros are nothing but number one zero is available at minus 0.4, then another one is available at plus j2, another one is available at minus j2. This is very important. So here from the expression itself, it is very clear that the highest power of numerator polynomial function is 3, because if you solve this equation here, you will get s square into s cube. That's why we must have 3 zeros for this particular system, and the same answers we are getting as an output. See, in this case we are having 3 zeros. One is available at minus 0.4, another one is available as at plus 2j, and another one is available at minus 2j. In the same way, let us do the calculations for pole. So calculations for poles. To calculate the pole, we need to equate the denominator polynomial function to 0. That's it. Because poles are nothing but those complex frequencies where the magnitude of transfer function is going to be infinite, and this is possible when the denominator polynomial function is going to be 0. So the moment we find the value of s corresponding to which the denominator function is going to be 0, if you put those values of s over here, automatically the value of this transfer function is going to be infinite. So if you apply that logic, here we need to equate denominator polynomial function to 0. So denominator polynomial function is nothing but s square plus 2. Then here we are having 1 plus 0.5s. This is going to be equals to 0. So equate this term to 0. So I can write here as s square plus 2 is equals to 0, or s square is going to be minus 2, or s is going to be plus minus j root 2, or I can write here as plus minus j. What is the value of root 2? It is 1.4142. That is very important. So two poles are available at this location, out of which one is at plus j 1.4142 and another one is at minus j 1.4142. In the same way, if you equate this particular term to 0, 1 plus 0.5 into s, this term to 0. So I can write here as 0 into s to be equals to what, minus 1, or s is equals to what, minus 1 divided by 0.5. So this will get cancelled and you will get s is equals to what, minus 2. So finally, we conclude that this system has three poles, out of which one pole is available at minus 2, another one is available at plus j 1.4142, and another pole is available at minus j 1.4142. Now what we need to do, we need to these poles and zeros in the S plane. That is the second objective of this numerical. See, our first objective is we need to find the values of poles and zeros. That is over. So here we conclude that the system has 3 poles and 3 zeros, out of which the poles available at minus 2, then plus minus 1.4142j. And in the same way, 3 zeros are available at minus 0.4 followed by plus minus j2. Now we need to indicate these poles and zeros in the S-plane. So how to represent them? So let me erase this. Now to indicate these poles and zeros in the S-plane, first of all we need to draw the structure. So the structure is something like this. We need to take two-dimensional axis. So on x-axis we need to take the representations like the real part, and on the y-axis we need to take the representations for the imaginary part. So here we need to take real part and here we need to take imaginary part. So real part positive has to be on right hand side, real part negative has to be on left hand side. Imaginary part positive has to be on upward, imaginary part negative has to be on downward. So here let us consider that this point is going to be 0. So here this is going to be plus 1, this is going to be plus 2, this is going to be plus 3, then here we are having plus 4, then plus 5, plus 6, and so on. In the same way, here we need to indicate minus 1, then here minus 2, somewhere over here is minus 3, then minus 4, then minus 5, minus 6, and so on up to infinite. Then on the imaginary axis, we need to take this as plus j, or you can say plus j1. Here we need to take plus 2j, this point. Then here we need to take plus 3j, and so on. And here we need to take minus j, then minus 2j, then minus 3j, and so on. So this is what the basic structure, and I want everybody to please draw this so that you can have a hands-on practice, that if you know the poles and zeros of the system, how to represent them on the S-plane. So draw the structure. So once you have done with this, now let us try to indicate the poles and zeros on the S-plane. Now first we are going to indicate the zeros. Now we know that this particular system having the transfer function indicated by this particular equation have 3 poles and 3 zeros, out of which first of all we are going to indicate the zeros of the system, and one zero is available at s equals to minus 0.4. And I told you that zeros are normally indicated by symbol circle, small circle, and poles are normally indicated by symbol cross. So this topology you need to indicate. So first 0 is available at s equals to minus 0.4. So minus 0.4 is somewhere over here. This is 0, this is minus 1. So somewhere over here we need to have minus 0.4. So let me indicate that 1 0 small circle is available over here. So this indicate s is equals to minus 0.4. This is your first 0. In the same way, one 0 is available at plus 2j and another one is available at minus 2j. This is very important. So plus 2j means over here. So one 0 is available over here and another one is available over here. So again these two, this one is indicate 1 0 available at minus 2j and this indicate another 0 available at plus 2j. Both are nothing but zeros. That's why we have indicated them or represented them in S-plane via circle, small circle. Now let us try to indicate the poles in the S-plane. So one pole is available at -2, and I told that poles are indicated by cross. So here we need to indicate cross symbol. So this indicate pole available at S is equals to what? -2. In the same way, another pole is available at J equals to plus J 1.4142. So 1.4142, that means somewhere over here. So here we need to indicate another pole available at S is equals to what? Plus J 1.4142. In the same way, one pole is available in between minus J and minus 2J because it is available at minus J 1.4142. So somewhere over here. So here we are having one more pole. So this indicate a pole available at S is equals to what? Minus J 1.4142. That is important. So this is very important. So in this way, we are in a position to indicate the poles and zeros of a given system on S-plane. The thing is that you need to apply this logic. If you have pole that are indicated by cross symbol, if you have zero that are indicated by small circle. The thing is that to find the value of pole, we need to equate the denominator polynomial function to 0, and to find the value of zeros, we need to equate the numerator polynomial function to 0. That is very important. Then the third objective of this numerical is that we need to calculate the magnitude of this particular system corresponding to some complex frequency. So how to solve that numerical, or how to solve the part of that particular numerical? So in this case, what we need to do is, our objective is to find the transfer function or the magnitude of the transfer function corresponding to some given complex frequency. And I think the complex frequency given to us is nothing but S is equals to 2. That means at S is equals to 2, we need to find the magnitude of this particular system. So again, it is very simple. What we need to do to find the value of transfer function at S equals to 2, we need to simply replace the value of S in this equation by 2 and solve for TF. So magnitude of transfer function, that is mod of TF at S is equals to 2, is given by, so I'm writing here as mod of TF is going to be equals to what? 1 by 2. So instead of writing S, now we need to replace them by 2. So 2 square, here we have S square. So this is going to be like 2 square plus 4. Then in second bracket, here we are having 1 plus 2.5 into 2. Then in denominator, we are having S square plus 2. So it is going to be 2 square plus 2. Then multiplied by 1 plus 0.5 into S. So S is replaced by 2. So if you solve this, it is going to be 1 by 2. Then here we are having 2 square, 4 plus 4, that is going to be 8 into 2.5 into 2, this is going to be 5 plus 1, this is going to be 6. 2 square is 4, 4 plus 2, this is going to be 6 into 0.5 into 2, this is going to be 1, 1 plus 1, this is going to be 2. So this 6 will get cancelled, 2 1s are, 2 4s are, then here 2 1s are, 2 2s are. So finally we got the magnitude of transfer function at S is equals to 2 is nothing but 2. So this is what our final answer is. I hope this numerical is clear to everyone. So through this numerical, we basically understand how to find the poles, how to find the zeros of the system, how to represent poles and zeros on S-plane, and then how to find the magnitude of the transfer function for a given complex frequency. This is very important. Now let us try to solve one more numerical on transfer function approach. And the numerical is like the reverse process that we just applied in the previous case. That means in the previous case, we know the transfer function and our objective is to find the poles and zeros, and then we need to indicate them on the S-plane. Now in this particular numerical, the pole zero representation of a system on the S-plane is known to us, and our objective is to find its corresponding transfer function. So how to do that numerical? So the statement for the numerical is the pole zero configuration of a transfer function is represented in the following figure, and the figure is given to us. So here we have the real part, and here we need to take the imaginary part, and the system has three pole. One pole is available at 0. So if you apply the same logic, cross indicate pole, small circle indicate 0. So one cross is available at 0, then one cross is available at -2, and then one more cross is available at -4. In the same way, zeros of the system are indicated by symbol circle, and one zero is available at -3. So this is what the numerical is given to us, and our objective is to find the transfer function of the system. Then the second part of the numerical is that we also need to find the value of overall gain k corresponding to the statement that the magnitude of transfer function is 3.2 at s is equals to 1. So at this particular condition, we need to find the expression for overall gain k. That is the second portion of this particular numerical. So how to solve this numerical? See, in this numerical, first our objective is to find the expression for transfer function. And how to find the expression for transfer function? Because to find the value of transfer function, we must know the poles and zeros. So poles and zeros representations are given to us in the S-plane via this particular figure. So through this figure, first we are going to find the poles and zeros, and then we are trying to find the expression for numerator polynomial function, then denominator polynomial function followed by k. Then we need to club them into the standard expression of transfer function to find out the value of tf. That will be the first part. And second part is that we need to find the value of overall gain k. The condition is that the magnitude of transfer function is 3.2 at s is equals to 1. So if you apply that logic over here, you can easily find out the value of gain k corresponding to this particular condition. So let me divide this particular numerical or solution of this numerical into two parts. In part 1, we are finding the transfer function of the system. And in part 2, once we know the expression of transfer function in terms of k, we are trying to find the value of k corresponding to this particular condition. So let us try to solve this. So first, from the figure, it is very clear that this particular system has only one pole, only one zero, and that zero is available at s is equals to -3. Why? Because I told you that zeros are indicated by symbol small circle, and here on the s plane we have only one circle, and that circle is available at -3. That's why the system has only one zero. On the other hand, we have total three cross. One cross is available at 0, another one is available at -2, and then another one is available at -4. That means this particular system has three poles, because poles are indicated by cross symbol. So first of all, I'm writing zeros of the system. So zeros of system. So 1 0 is available at -3. So I'm writing here as s is equals to what? -3. Or if I shift this particular term on the left hand side, I can write here as s plus 3 is going to be equals to what? 0. So this will be the component of your numerator polynomial function, because to find the value of 0, what we need to do? We need to equate the numerator polynomial function to 0. That's why it has to be on the numerator side. In the same way, what about poles? Poles of system. So here one pole is available at s is equals to 0. Then one pole is available at s is equals to what? -2. Then one pole is available at s is equals to what? -4. So I can rewrite this as s plus 2. This is going to be equals to what? 0. And here I can rewrite this as s plus 4. This is going to be equals to what? 0. That is very important. Or if I am interested to write the expression for denominator polynomial function, because poles are find out by equating denominator polynomial function to 0. So we need to club these three components simultaneously. So one pole is at s, then another one is at s plus 2, another one is at s plus 4, and this entire term is going to be equal to 0. So this is going to be the denominator polynomial function, whereas this is going to be the numerator polynomial function. I hope this point is clear to everyone. Now what we need to do? We need to write the expression of transfer function by considering the numerator polynomial function as well as denominator polynomial function, followed by general expression for gain k. So I told you that the mathematical representation for transfer function for any physical general system, it is nothing but like tf is going to be equals to overall gain k multiplied by numerator polynomial function, and then we need to take in the denominator side denominator polynomial function. I hope this point is remembered by everyone. So see here, if you apply that logic, so I can write here as transfer function is going to be equals to overall gain k multiplied by numerator polynomial function. So what is numerator polynomial function? It is nothing but s plus 3. So here we need to take s plus 3 whole divided by denominator polynomial function, and the expression for denominator polynomial function is s into s plus 2 into s plus 4. So I can write here as s in bracket s plus 2 in bracket s plus 4. That's it. So this indicates your equation number 1. Let this will be your equation number 1. So equation number 1 indicate what? The expression of transfer function of a system whose pole 0 representation in S-plane is known to us. And from this pole 0 representation of a system in S-plane, we have find out the mathematical expression of transfer function, which is nothing but k times s plus 3 whole divided by s into s plus 2 into s plus 4. I hope this is understood by everyone. Now, the second part of this particular numerical. And what is the second part? We need to find the value of k corresponding to the condition that the magnitude of transfer function is 3.2 at s is equals to 1. That means the moment you put s is equals to 1 in equation number 1, the magnitude of transfer function is going to be equals to what? 3.2. And for this condition, you need to find the value of what? Gain k. That's it. So if you apply that logic over here, let me erase this part. So if you apply that logic over here, I can write TF is nothing but 3.2. So 3.2 corresponding to the value of s we need to replace by 1. So here we need to take gain k multiplied by s plus 1 or s plus 3. So s is nothing but 1. So it is going to be 1 plus 3 whole divided by s into s plus 2, s plus 4. So s is nothing but 1. Then multiplied by s plus 2. So it is going to be 1 plus 2. Multiplied by s plus 4. It is going to be 1 plus 4. So this is going to be k times 4 whole divided by 1 into 2 plus 1, that is 3, into 4 plus 1, that is going to be 5. Or if you write this as k, so I can write this as k equals to 3.2 into 5 into 3, this is going to be 15 divided by 4. Or if you solve this, I can write this as 4 tens and 4 eights, 8 fours. Then this is going to be like 4, and then this is going to be 5. This is 5 ones, 5 threes, and finally we have 4 into 3, that is going to be 12. So finally the overall gain of the system is 12 at s equals to 1, and the magnitude of transfer function corresponding to s equals to 1 is nothing but 3.2. So instead of writing this k, now what we need to do? We need to replace this k by 12. So the final expression of transfer function is like this. So instead of writing this k, now we need to replace this k by 12. That's it. So here the overall gain k of the system is nothing but 12. So the expression of transfer function now, it is 12 into s plus 3 whole divided by s into s plus 2, s plus 4. And from this equation, it is very clear that the overall gain k of the system is nothing but 12. It has 1 0 available at s equals to minus 3. The same is indicated over here. And then it has 3 poles. One pole is available at s equals to 0. See, s equals to 0. Another one is available at s equals to minus 2, and then s equals to minus 4. See, s equals to minus 4. So this is another way of solving numerical on transfer function. The thing is that in this case we have the representations of poles and zeros in the s plane, and our objective is to find the corresponding transfer function or the mathematical expression of transfer function, and then we need to find out the value of k corresponding to some given conditions. Now let me give you one example in the homework, and your objective is again to find the value of transfer function. And the numerical is something like this. Here we have the representation of a system in the form of circuit diagram like this. So here we have a resistor, of value capital R, and then here we have connected a capacitor of value C, and uh, across this particular structure we applied some input excitation in the form of E1 or EI. This is going to be the input, and corresponding to this we are getting some output in the form of E0. So this is going to be the output of the system output. And in this case your objective is to find the transfer function of above system. How to find the transfer function of above system? That you need to think. Again, it is very simple. The thing is that you need to apply some logic over here. Let us assume that the value of current flowing through the circuit is in clockwise direction. Write the expression of the circuit component by applying KVL. So I voltage across resistor is nothing but your R into I, and then voltage across capacitor. We know the expression for current flowing through capacitor, I equals to what? C dV by dt. So we can write V as integral I 1 upon C integral I of dt, and then apply the logic, because these equations are in time domain. Convert that from time domain to frequency domain by applying the logic of Laplace transform, and then take the ratio of output by input, because ultimately what is transfer function? It is nothing but the ratio of output by input in frequency domain. That's it. So ultimately the transfer function is going to be like capital E naught of S divided by capital EI of S. This you need to find out. That's it. So this is one approach. Second approach is that directly you can convert this particular network into corresponding frequency domain. And how to convert that? Again, you need to apply the applications of the transfer function. Like the same circuit I can draw like this. So here going to have resistors followed by capacitor, but in order to convert the system from time domain to frequency domain, resistor will remain unchanged. So because resistor is frequency independent component, so it is going to be remain R. But here instead of writing C, now we need to write here as 1 upon Cs. This is very important. And then this small ei of t is going to be equals to what? Capital EI of S. And here the small e naught of t is going to be equals to what? Capital E naught of S. And then it is very easy to find the ratio of E naught of S by EI of S. The thing is that you need to apply voltage division formula over here directly. We can find the relationship between E naught of S followed by EI of S. That's it. So if you apply that logic, you can easily find out the uh, expression for E naught of S by EI of S. So I gave you the hint to solve this particular numerical. You may apply this logic or you may apply this logic. In both the cases, you will get the same answer. In first case, what you need to do, apply KVL, solve the network in time domain, and then apply Laplace transform to convert that from time to frequency domain, and then take the ratio of output by input. Or in the second case, directly convert the network into frequency domain by applying the concept of what? Laplace transform, and then solve this particular network by applying KVL, KCL, or you can apply any kind of circuit tool analysis technique to find out the relationship between E naught of S by EI of S. Let me tell you the final answer, what you will get. The ratio of E naught of S by EI of S in this case is going to be like 1 upon R into C into S plus 1. This you will get as a final output equation. Or I can write this as 1 plus R into C multiplied by S. So this will be your final transfer function for this particular system. Your objective is to solve this as an homework. So in the next class, we will start another topic of our course that deals with the concept of signal flow graph. Signal flow graph. Now, from the next lecture onwards, we are going to understand how to find the transfer function of a system, because up till now what we have discussed, that what information we can get from transfer function, what is the importance of transfer function, why need to calculate transfer function. Now in the next lecture onwards, we are going to focus on what are the different types of technique through which, if we have a system, how to find the transfer function of that particular system. Maybe that system is available in the form of graph, maybe that system is available in the form of some mathematical equations, maybe that system is available in the form of circuit like this. In this case, we have the representation of system in the form of circuit, and our objective is to find its transfer function. So what are the different types of technique which are available with us through which we can find the value of transfer function or the expression of transfer function for a given system, that we are going to find. And once we know the value of transfer function, then in the remaining portion of the course, we are trying to find how to check the stability, how to find the time response analysis, how to find the frequency response analysis of the system if we know the transfer function of that particular system. Thank you.